Okay, so what we're going to go over today is how energy gets transferred on Earth. All right, that's kind of the start of it, because this whole unit is on energy transfers in a global system. What we want to go over today are the mechanisms that make that happen. All right, we're going to look at the 3 parts of the Earth, and how they contribute to the movement of energy from place to place. We're going to look at the ways that energy moves within the 3 parts of the Earth, how effective that is, right? And we're going to look especially at the 3 fates of light that encounters the Earth. Okay, the 3 fates of light when it encounters the Earth is it's either going to be absorbed, it's going to be reflected, or it's going to be used. Okay, all right. What are the 3 parts of the Earth? If I could break the Earth up into 3 sections or 3 pieces, what would they probably be? Water, land, and air, right? Okay, so we're looking at essentially the 3 spheres, okay? That is the hydrosphere, all the water on Earth, the lithosphere, the solid parts, stone and earth and soil and things like that, okay? And the atmosphere, all the gases that surround the Earth. Which one do you suppose is most important for transferring energy from place to place? Okay, water can do some of that, but water's not in contact with all parts of the Earth. What is? The atmosphere, right? I mean, really, guys, where does all weather occur? In the atmosphere. And weather and wind and things like that are the mechanisms by which energy is transferred from place to place. The other reason is the atmosphere is the most fluid of the 3 parts of the Earth. Okay? I mean, obviously, the solid part, the lithosphere, is solid. Right? It's not going to change shape. It can't move around, okay, things like that. The water is obviously fluid, but doesn't touch everywhere. The atmosphere is even more fluid than water. Okay? Gases are more fluid than water. They can change shape easily. They can move easily. Okay? So the bulk of our energy transfers and absorption occurs in the atmosphere. All right. Why is the sky blue? Okay. That's usually the answer I get because I know that somewhere along the way you were taught that. Okay, but it actually isn't true. What color is the ocean? Not blue. It's clear. Okay, the ocean looks blue because it reflects the sky. The sky is blue because it scatters blue light. Right. So when light comes in to the Earth and hits the atmosphere, there's a spectrum of light, okay? And part of that is the visible spectrum that we can see, the colors of the rainbow, right? The colors are based on wavelength of light. Blue light has a really, really short wavelength. Red light has a longer wavelength. Heat waves, which are infrared, have an even longer wavelength than red. That's why they're infrared, okay? And ultraviolet is even shorter than violet. Everybody follow there? So there's a spectrum of light, okay, that we can measure. Blue light has really short wavelengths and gets scattered by the gases that make up our atmosphere. That means it bounces around all over the place and appears to make the sky look blue. Now, at sunset, is the sky blue? Why not? Well, actually, I mean, it's the same wavelengths, but you're on the right track. Okay, when the sun drops down near the horizon, it's not going through the cleanest parts of the atmosphere anymore. Now it's down near the surface where there's particulates like smoke, pollution, okay, things like that. Those scatter longer wavelengths like orange and red and yellow. Okay, so the sky typically appears orangish red at sunset because the light from the sun is being scattered differently. Okay? If we get like a big dust storm or something like that where there's a lot of dust in the sky appears a different color, right? It scatters the light differently. Right? Most of the time it scatters it so it appears blue. Okay? And you notice this with the moon as well. If you ever watch the moon rise, because you shouldn't stare at the sun when it's rising, okay? But if the moon's rising, when the moon is lower on the horizon, it not only appears bigger, but it usually appears yellower. When it gets higher in the sky, it looks smaller and whiter. Okay, next time just have a look because the moon's pretty big right now. It was like full 2 days ago, I think. Okay, so if you look at it now when it rises, okay, you'll notice it's quite a bit of a different color, okay, near the surface. Okay, so in terms of the 3 things that can happen to light, it can be absorbed, it can be used, it can be reflected. Okay, right now, the ground outside's covered in snow. Okay, what does snow do to light? Or what do all white things do to light? They reflect it. Light colors reflect more than dark colors. Right? So right now, not a lot of the pathetic amount of solar radiation that we're receiving, because it's December, okay, is getting absorbed. Most of it's getting reflected off the surface because the surface is covered in white snow. Right? So it kind of exacerbates the problem here in that we've got very little light coming in, and what we're getting is all getting reflected. Right? In the summertime, obviously the ground is covered differently. Okay? There's no snow, there's plants there, so a lot of the light gets absorbed or a lot of the light gets used. How do plants use the light? To make food. What's that process called? Photosynthesis. Okay, so these are the three things, and these are three that you're going to have to know. Okay, if it's getting used, okay, that means it's by photosynthesis. There's only one set of organisms that can directly use sunlight on Earth, and that's the photoautotrophs. If you think back to the biology unit where we talked about that, okay, those are the only ones that can use the only source of energy we have on Earth, okay, is the sun. So when the sun's light comes in, the only way that a food chain or anything like that gets started is if there's plants there to convert that solar energy into chemical energy that other organisms can consume. Everyone all right with that? Okay. Now, I just said a few minutes ago that all forms of energy on Earth come from the sun. Okay. Is that really true? Actually, it is. Believe it or not, it is. Okay. Even nuclear energy. Okay, nuclear energy didn't necessarily come from our sun, but they were heavy elements that were created in the core of a larger star that went supernova and made all the stuff that made our solar system. That's 16 billion years ago, whatever. Okay, but it still came from a star at some point. Okay, even the fossil fuels that we burn in our car were at one time solar energy. Okay? They're fossil fuels because they came from plants that captured solar energy by photosynthesis and converted into sugars, and then they died and got buried and turned into oil and gas and coal and things like that. Okay, so I don't think Rachel Notley's going to accept the argument, but okay, we could say that coal is really just solar power after 500 million years. I don't think she's going to buy it, but okay, it's true. Okay, if someone gives you a hard time about driving a big truck, you can tell them, "Oh, my truck is solar powered," and they'll probably leave you alone because they'll think you're weird. Okay, but yeah. All right, is that making sense to everybody? Okay, so that's what happens when it gets used. If it gets absorbed, what's going to happen to the temperature? If you absorb mechanical energy, then your energy has gone up. If you absorb thermal energy, does your energy go up as well? Okay, and we'll see that as a change in, how do we measure thermal energy? Heat, how do we measure heat? Starts with T. Temperature, yeah, okay. We'll see a change in temperature. If energy gets absorbed, there's going to be a change in temperature. All right. And you can see this on like a hot day. If you have like a car that's black on the inside, right? It gets really, really hot on the inside of that car. Whereas if you have a lighter color interior, it's typically not quite as hot, reflects more light away. Okay, so reflection is going to result in basically no change in temperature. Absorption is going to result in a change in temperature, right? So those are the three things that can happen. Okay, so the three parts of the Earth are atmosphere, hydrosphere, lithosphere. And we said the atmosphere is the most important for transferring energy. Should probably write that down. The atmosphere is the most important, okay, in terms of transferring energy on a global scale. The atmosphere is made of many layers, the names of which I'm never going to ask you about, so don't bother memorizing them. Okay, they're not important. I'm not going to ask you troposphere, stratosphere, exosphere, mesosphere, any of that. Okay, but what they do in terms of what they do to light that's coming in is important, and what they do in terms of supporting life on Earth is also important. We live in what's called the troposphere, okay, which is the bottom layer, okay, and that means that all the gases from above are being pulled down by gravity against the surface of the Earth. Okay? In the troposphere is where they're the most dense. Okay? What does gravity pulling on the atmosphere make us feel? Or what does that create? It's pretty important for us. Is it what? Yeah. It is. It's weight. Yeah, mass has to do with how much of you there is. Weight is gravity pulling on your mass. So if you've got all of this atmosphere being pulled down by gravity, what are those gases exerting on you? Force, pressure. Okay, the gravity pulling down on the atmosphere creates what we call atmospheric pressure. Without atmospheric pressure, life on Earth would be impossible. Okay, if you go out into space, there's no atmospheric pressure. Okay, bad things happen if you are out in space without a suit. Right? Our bodies are dependent on atmospheric pressure. And you can feel changes in atmospheric pressure if you've gone down like a really big hill really fast or up a really big hill really fast. What happens to your ears? They pop. Okay, why? Because there's less pressure on the outside than there was on the inside. And until you make that pressure equalize by swallowing a couple of times, okay, and allowing the little eustachian tubes that are inside here, okay, to balance the pressure, you feel pressure on the eardrum because there's more pressure either on the outside pushing in on it or more pressure on the inside pushing out on it until they balance. Okay, when it pops, and it's like, oh, that's so much better. Right? That's what causes that is atmospheric pressure or changes in it. The higher up you go, the less atmospheric pressure there's going to be. When there's less atmospheric pressure, gases behave differently. Okay? Normally, like right here on Earth, okay, with normal 1 atmosphere pressure, the gases in our blood, okay, like nitrogen, that's the biggest one, okay, oxygen, carbon dioxide, all those, okay, they stay dissolved in our blood. If we rapidly change pressure or altitude, okay, then some of those gases might try to leave the blood. Okay? And if they do, they turn into bubbles. Okay? Is having bubbles in your blood a good thing or a bad thing? It's bad, yeah, because bubbles can lodge in your blood vessels and block them. Okay? And if they block them, what happens to all the blood behind? Well, you might get a clot or you might just get enough pressure to break the vessel. Okay? If that happens in your brain, that's like having a stroke or an aneurysm. Okay? It's a brain bleed. Okay? And so blood vessels in your brain break, and then the parts of the brain that are supplied by those blood vessels starve. Okay, they suffocate, they starve because they're not getting the stuff they need. That's what happens in a stroke. Okay? If someone has a stroke, that's what's going on. And those parts of the brain essentially die. Okay? So obviously we don't want that to happen. Okay? So we have to be careful about our atmospheric pressure. Okay? Because gases do behave differently. It's really weird. If you watch anything on like climbers and stuff like that, when they're climbing up Mount Everest or K2, the really high mountains, when they try and make food, like soup and things like that, water boils instantly, okay? Because the higher up you get, the less pressure there is on water, and it wants to turn into a vapor more easily. The boiling point of water at like Camp 4 on Mount Everest is about like 58 or 60 degrees, okay? Not 100 like it is at sea level. So they basically have to eat the soup on the burner, on the stove, boiling. Because it's boiling at 68 degrees or whatever. It's like way lower, right? You could eat the boiling water, not like you could at sea level, okay, or here for that matter, because it's about 98 degrees here. Okay, everyone following on that? So if water can evaporate that easily, can it evaporate easily from tissues in your body as well? Okay, and that's a big deal for them. They lose a lot of fluid through evaporation, so they have to stay well hydrated, but they also have a problem in that with less pressure to keep it there, fluid can accumulate in your lungs. Right? And if you stay above about 27,000 feet, okay, you're in what's called, anyone know what that's called when you're above 27,000 feet? And climbers call it the death zone because you are slowly dying at that altitude. Your body will not function up there for more than maybe a couple of days. Okay? Because the gases are trying to leave your body. You're getting fluid building up in your lungs. You can actually drown, okay, in your own fluid in your lungs at that altitude. It's called pulmonary edema. It's very bad. Okay? So they have to be very cautious of how long they stay above that altitude, especially if they're doing it without oxygen. And if you have supplemental oxygen, it's a little bit better, but that's, again, changing pressure, right? You can put that mask on and get different atmospheric pressure from the tank. Okay, so all of these things are really important for us in terms of survival. If you're out in space and you go outside without a spacesuit on, what'll happen to you? Yeah, everyone thinks that you're going to pop because that's what science fiction has told us will happen, right? And your eyes will explode, and actually they will rupture. They won't pop, but okay, the fluid inside does start to boil and stuff, so that would be gross. But yeah, you can actually survive in the vacuum of space for over a minute. Okay, a minute 30 is kind of the cutoff for you having any hope to survive. You won't be pretty after that, but okay, you can survive beyond that. Okay, but you don't stay conscious for that entire time. It becomes pretty painful and you get oxygen deprivation and you kind of pass out before that. But yeah, it's about a minute and a half that you could survive in the total vacuum of space. But it's hard on the body. And you would have to be in a hyperbaric chamber for quite a while after that. Okay, that's those big, well, it's a big tube essentially that they can change the pressure in and try and force the gases back into your blood properly. Yeah. Scuba divers get it if they come up too quickly, right? If you've heard of the bends, that's kind of the opposite. It's going from high pressure to low pressure really quickly, and you can get those oxygen bubbles lodged in your muscles. It's very painful. Okay, so it's something that we have to certainly appreciate that the atmosphere does for us. Okay, the other thing is that the atmosphere, like we said, scatters certain kinds of light. Okay, it scatters the blue light. Well, the ozone layer and things like that also scatter and reflect harmful rays that would cook us, literally, if they weren't there. Okay, so we have the ozone layer that protects us from ultraviolet light, scatters it and reflects it. Okay, the upper layers of the atmosphere also protect us from things like X-rays and gamma rays. Okay, because contrary to what Marvel Comics would tell you, gamma rays will not turn you into the Hulk. Okay, they'll just cook you like an egg on a pan. Right? We don't want to have those. Okay, they're very high energy, so they get thankfully reflected and scattered and removed by our atmosphere. If you were out in space, you would be fully exposed to those types of things. Even on the International Space Station, they do occasionally get hit by cosmic rays that contain that kind of stuff. Okay. Now, the other function of the atmosphere is to help with this absorption, reflection, and, well, not so much the use, but absorption and reflection of light. Okay? As the long wave radiation, okay, the stuff we can see, and the heat, infrared, comes through, it's going to strike the Earth. Some of it will get absorbed, and some of it will get reflected. The stuff that's reflected tries to get back out into space. Does it always? What can it sometimes reflect off of? People are all worried about it. Not the ozone layer. That's a good, well, the hole in it is bad, but it's actually closing up now. You guys heard of the greenhouse effect, right? Okay, right. Greenhouse gases are naturally present in the atmosphere, and it's a good thing they are. With no greenhouse effect, the Earth would be like Mars. It would be freaking cold, like it would just be awful. Okay, but a lot of those long waves reflect off of the greenhouse gases, and they come back down. They keep the Earth warm. Okay, so it's important to have that. Obviously, we don't want it to increase too much because that could lead to global warming and things like that. But a bit of greenhouse effect is necessary. Too much is a bad thing. Okay, like if you look at Venus, for example, okay, Venus's atmosphere is entirely carbon dioxide. It's 100 times thicker than ours, and it has this incredible greenhouse effect that traps basically all light. Okay, that gets through. So if it gets through the cloud layer, it hits the surface, tries to get, doesn't get back out into space, and the surface of Venus is like the inside of an oven. Okay, it's about 400 degrees Celsius. Right? And then Mars is the opposite. Okay, it's got 1/100th of our atmosphere, can't trap any heat at all. Okay, and so energy just bleeds away. Okay. So the atmosphere plays a critical role in maintaining the Earth's temperature, which in turn has an effect on climate. Okay, if we didn't have the greenhouse effect, our climate would be a lot different. Okay, much of the incoming solar radiation is reflected away from the Earth by particles like water vapor and ozone. If it's a cloudy day, is it generally cooler on a cloudy day? Because the tops of clouds are what color? White, and they're reflecting away a lot of the energy, so it doesn't reach the surface, so it's cooler. Okay, so they're reflected away by the Earth by particles, okay, and by the reflectivity, or, and this is going to be an important term, albedo of the Earth's surface. Okay, the term albedo describes the reflectivity of the Earth's surface at any given place. Now, can that change? Yeah, okay, the reflectivity or the albedo of the area outside the window here can change from summer to winter or whatever. Okay, comparing, right, in the wintertime where it is right now, okay, about 85 to 90% of all the incoming solar radiation that hits the snow gets reflected off, and less than 10% is absorbed. In the summertime, 70% gets absorbed, okay, and then 10% can be reflected off of liquid water, okay, and about another 20% gets reflected off of like just the surface of the Earth, right? So are we getting a lot more absorption in the summer? We are, okay, way more absorption. And included in that absorption would be plants absorbing that light and carrying out photosynthesis. right? So albedo is how reflective is the Earth's surface, okay? A high albedo means high reflectivity. So this would be high albedo here, okay? And this would be low albedo over here. Okay, do we use this property to our advantage at any point? Especially in the wintertime, we do something that tries to change albedo on the roads. What do we put on the roads when it gets icy? Okay, salt and gravel, sand. Okay, the salt will lower the melting point of water a little bit, okay, but it's only going to be a few degrees. What really helps melt the ice is the fact that when we throw sand on the ice, its albedo goes down, right? It gets darker and it's going to absorb more solar radiation. So you combine a little bit of salt and some sand, and you suddenly got a recipe for making ice and snow melt at a much lower temperature than they normally would. Right, so that's the whole reason for doing that. Now, the added advantage of throwing sand on the road is that it also increases traction. Okay, it's less slippery than ice, but it's got all these other benefits as well. Okay, it helps to melt that ice a little more quickly, okay, because it helps it to absorb more solar energy. What color are our roads in general? Yeah, I mean, when they're brand new, they're really black, okay, but they stay kind of grayish, kind of dark gray most of the time. Is there a reason for that? Yeah, they fade, the sun bleaches them out, but we want them to be dark. Okay, we want the road to be dark because if it's dark, it'll absorb more energy. Okay? If you go to other places, the color of roads actually changes from place to place. Have you ever been to PEI? The roads are red. Yeah, Florida, yeah, yeah, really black. Okay, but and if you go to California, they build their roads out of cement, out of concrete, because if they built them out of asphalt, which they used to do, they would get really soft because of all the heat that's there. Okay, they could absorb a lot of energy. They'd get soft. I remember as a kid, we drove down to Disneyland in our truck with a camper, and we got a flat tire. My dad pulled the jack out and started jacking up the truck. He was just able to loosen like 2 lug nuts on the tire, and the tire was back on the ground. And he thought there was something wrong with the jack until he went over to the jack and noticed it had sunk that far into the road. Okay, like it was that hot. The asphalt had gotten so soft that the weight of the truck pushed the jack down into the asphalt. Okay, that's how in a lot of places you get that the grooves in the road. You guys maybe haven't driven enough yet to notice this, but lots of times at intersections the road has this hump in the middle, okay, because people's tires and weight is always in one spot. When the road's warm in the winter, or warm in the winter, warm in the summer, okay, it actually gets a little softer and we can push it down a little bit. Okay, so typically in some places where it's really hot, they make their roads out of different material so that it doesn't get quite as hot. Okay, in Arizona, has anyone ever watched the death race in Arizona? These crazy people who run through the desert in the middle of summer. It's nuts. When they run on those roads, they actually run right on the white line. Because if they don't, their shoes will melt. It's wild. Okay, if you ever watch them, these people, and they're running like normally you run with your feet beside each other. They run like this, like they're running on a tightrope. Okay, so they can stay on the white line because the white line is cooler than the rest of the road. Okay, and there's the rubber on the soles of their shoes after hours and hours because they run all day in the blinding heat. The rubber gets so soft in the shoes it literally just melts off. Okay, so albedo, pretty important. Okay, in some cases it's good. In some cases, okay, it's absorbing too much energy. All right, so make sure you know that term. That's going to come up lots. Okay. And then in this diagram here, we're showing some of that incoming radiation is getting reflected by clouds. Okay, some of it's getting absorbed by the atmosphere. Some of it gets absorbed by the Earth. Okay? It's important for the atmosphere to absorb some radiation. That's how it increases in temperature. Okay, and then we've got some of that stuff that's outgoing. It actually gets all the way out of the atmosphere and back out into space. Okay. Do we give off heat waves? Yeah, all hot objects do. Okay, and our body temperature is 37 degrees. That's why those night vision cameras work. Okay? If anyone's ever seen the police shows where they chase people, okay, and they've got the FLIR on the helicopter looking for them, right? They stand out. They're just white against a black background, right? Because you're giving off all of this solar radiation. Now in the wintertime, we don't want that. We want to keep all that solar radiation in, so we put on heavy coats and things like that that help to insulate us. What else could we do? Like if I want to keep warm and it's dark outside, What color should I wear? If I want to keep warm and it's light outside, I want to wear black because black will absorb a lot of light. But if it's cold outside and there's no light, it's dark, it's nighttime, what color do I want to wear? White. I want to reflect my own heat back on me. Okay? If you've ever opened up the survival blanket in a survival kit, okay, it's like, especially the ones that come in the little package about this big. What are they made out of? You guys never seen one of those? They're like tin foil. Okay, they're just shiny foil. You wrap yourself in that, and it reflects all of your infrared radiation that you're giving off back onto you. Okay, it's not an insulating blanket like a real blanket would be. Okay, it's just a reflective emergency blanket, and it can help to keep you quite warm, actually. Right? How many people have ever baked potatoes on the barbecue? Okay, you ever notice that there's two sides to tinfoil? One side is dull, one side is shiny. I've been to a lot of barbecues. It is quite clear that a lot of people don't know that, because I watch them wrap their baked potatoes and I'm like, okay, I want that one, because that's like one of the few you wrap the right way. Okay, what side needs to be out if you want to bake a potato properly? Dull or shiny? Dull. The dull side absorbs the energy from the barbecue. If the shiny side is facing in, then the heat goes into the potato, through the potato, and hits the shiny side of the foil on the other side, reflects back through the potato, cooking it properly. Then you don't get that nasty half-cooked potato off the barbecue that's been on there for an hour and a half because somebody wrapped it the wrong way. Okay, you always wrap the tinfoil dull side out. Now you know. Now you won't be embarrassed at a barbecue. Okay. Okay, so atmosphere and climate. So we've already talked about the gases here. Okay, these are some greenhouse gases. Carbon dioxide, obviously everyone knows that's a greenhouse gas. Everyone's afraid of it, but it's actually not all that bad. Okay, CFCs, okay, they're a pretty small kind of greenhouse gas. Methane, where does that come from? Yeah, cows. Yeah, and us too. Okay, anything that farts, okay, makes methane. Okay, methane is in all of that. There's a lot of bacteria as well that create methane. They're actually the biggest producers of methane, but it's a greenhouse gas as well. Okay, ozone, nitrous oxide, all of those allow the radiation to come through. Okay, but after it strikes the earth, it changes slightly, gets a little bit longer, and then it gets trapped by that greenhouse gases. Okay, also the other day I found this picture. It has nothing to do with this. It's a picture of the rain shadow effect we talked about the other day. Okay, when moist air masses get pushed up and over a high mountain, okay, they drop the precipitation. This is Mount Robson, the same one I showed you before. But lots of times you can't see the top of Mount Robson because it's high enough that when moist air gets near it, it goes over the top and forms a cloud just around the top of the mountain. So the top of the mountain is often in cloud, even if the rest of the area is clear. Okay? And you can sometimes see, if you're watching, it'll be clear, 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 and then all of a sudden this cloud will appear out of nowhere on the top of the mountain because some more moist air mass has been pushed up and over. And then it'll pass, it'll be gone after an hour or two, and there'll be a fresh coating of snow on the top of the mountain. Okay? So it's just showing you kind of the localized rain shadow effect of a tall mountain. Okay. Okay, should we know what this is? Okay, because that's probably something you'll want to talk about. You know, if I give you a question on a test about energy transfers or trapping of energy, greenhouse effect would be a good thing to mention there. All right, the hydrosphere, all the water, okay, liquid water on the surface of the Earth. Okay. Can the ocean play a part in our climate? Sure it can. We're seeing it right now. We saw it last year when we had El Nino, and this year with the mild La Nina that we're having. Okay, we can see that the ocean can globally affect the temperature and weather climate-wise on the Earth. Okay, now for the hydrosphere, okay, we include water vapor and ice, but they don't do a lot in terms of energy transfer. It's the liquid water, okay, that's doing a lot of the transfers. The water vapor we include because it's more part of the atmosphere, and it's part of something called latent heat. Okay, there's sensible heat, the kind we can feel, and there's latent heat, the kind that's there but we can't feel it. What latent heat is the energy stored in materials because of their state. Okay, steam contains more energy than liquid water does, right? And probably some of you are going, well, obviously steam's hotter, but steam and water can both exist at 100 degrees Celsius, just like ice and water can both exist at 0. But steam at 100 degrees contains almost exponentially more energy than liquid water, because energy is required to change water from liquid to gas. That energy stays in there as what we call latent heat. If that steam condenses back into a liquid form, all of that energy gets released. Okay, which is why you probably heard steam will burn you way worse than water. Okay, it's true. Even if they're the same temperature, even if the steam's only 100 degrees Celsius, it'll burn you way worse than liquid water at 100 degrees, because not only is it 100 degrees, but when it hits your skin and then condenses back into a liquid, it will release all the latent heat that it had stored previously. When it releases it, it becomes sensible heat. Okay, that's what can burn you. All right, so that's something to watch for. Okay, it's also the reason we put ice in drinks. Okay, if you want to keep a drink cold, you put ice in it. Okay, because ice, once you put it in the drink, it pretty much is 0 degrees, but it'll stay there until all of it is melted. And the temperature of the drink will stay around 0 until all the ice is gone, because ice takes a fair amount of energy in order to melt. Okay, so it just keeps absorbing energy from your drink and keeping the drink cold for however long. Okay, so less than 0.1% of all the water that's evaporated from the surface of the earth is returned to lakes, rivers, or streams, or seeps into underground hollows. The rest returns to the ocean or is frozen in ice caps. And not the kind you get from Tim Hortons, okay? The kind that are on the tops of mountains and poles. All right, everybody, does that make sense to everybody there? Okay, if water evaporates from here, it's highly unlikely it's coming back here. Right? If we get rain here, it's not because that water evaporated from here. It probably evaporated from hundreds or thousands of kilometers away. Okay? The atmosphere is always moving around. Okay? And so it's very easy for water and water vapor to make their way to different places. Okay. If water gets frozen in an ice in a polar ice cap or a glacier or something like that, is it lost? Okay, so it's still there, and eventually it'll be released. Agreed? Okay? And we're releasing quite a bit of it right now, right? The glaciers are all shrinking, and they're shrinking quite rapidly, actually. All right, how many times have you guys seen the water cycle? Lots, right? Lots and lots. So this is probably the last time, but we go over it again, but this time in terms of where's the energy coming from, things like that. Okay, so we'll start with water in a liquid form, either in the ocean or from plants, whatever. Okay, when sunlight strikes the water or strikes the plants and plants carry out photosynthesis, water evaporates. We talked about that in the biology unit. Okay, we call that evapotranspiration. Okay, evapotranspiration is the evaporation of water from plants as they carry out photosynthesis. Okay, if light strikes the ocean, then some of the ocean water is just going to evaporate. This now represents a lot of energy being put into the atmosphere, because the water vapor, which takes a lot of energy to change state from liquid to gas, is now in the atmosphere and moving around. If it goes to another place and condenses, all the energy that it stored or possessed will be released in that new place. Okay, so latent heat, this energy stored in water vapor, is a big mechanism for moving energy around on Earth. Okay, because we said the atmosphere is always moving, water is always moving with it, water vapor is always moving with it, and that can transport large amounts of latent heat. All right, so we get water vapor into the atmosphere. Eventually it's going to condense and it's going to fall as precipitation. Okay, that precipitation can be in any form. Okay, snow, rain, hail, whatever. Right, some of it will run off. That is, it gets into the rivers and it ends up back in the ocean. Okay, some of it will be in freshwater storage on the surface, lakes, wetlands, swamps, bogs, okay, things like that. And some of it gets absorbed. Okay, the absorption we call infiltration. It's kind of hard to see on there, but it's called infiltration. The process is similar to how you make coffee. You pour water through the coffee grounds and it goes through the spaces essentially in between. Okay, that water can go very deep into the Earth's kind of crust. Okay, and what we call that is underground storage. Okay, so we call it water storage, but it's underground or groundwater storage. How many people have a well at home? Okay, draw their water from a well? Nobody? Okay. Water gets stored underground in what are called aquifers. You tap an aquifer with a well. Okay, and if there's enough water in the aquifer, there's pressure that'll push it up, and you don't even have to have a pump. Okay, it'll just come right out. So that's what we access when we get drinking water. Okotoks, most of Okotoks' water is actually from wells, aquifers that are near the river. Okay? The river recharges them, okay? But we get most of our water actually from wells and groundwater, and that's the drinking water source for most cities in North America, at least. Right? Why don't we use the river for drinking water? How many people are in Okotoks? Like 25 or 26,000 now, right? Like it's big. If we had to take all of our water to supply all of those people out of the river would be a pathetic little trickle on the other side of Okotoks. Okay, that's how much water we would pull out. The Sheep River simply can't, with its flow, supply an entire town. That's why we also use wells around the town. Okay, it's also why they couldn't get the that Mike Holmes community on the other side of Highway 7 that they wanted to build. They couldn't get the rights to do that because there wasn't enough water. They actually had to find a place that had an aquifer and buy the water from them, okay, or buy the rights to access that water. Okay, so it's something that comes up fairly often. Okay, so there's infiltration, which supplies us with groundwater. So the cycle just goes runoff, okay, water storage, evaporation, condensation, precipitation, and then sometimes you get infiltration, storage, runoff, okay, and it just keeps going around and around like that. Okay, these are the processes that require energy. These are the processes that give it back. Okay, and that can be important when you're far from the equator like we are. A lot of the energy that comes here isn't necessarily just from the sun directly. It's from the sun evaporating water at a more equatorial latitude and having that water vapor move up here and condense. Okay, so we get a lot of that latent heat up here. Okay, and of course, all the water is conserved. Okay, no drop of water has ever been completely lost, okay, from the earth. The water cycle makes sure that all of it is there. Okay, so you sweat and it evaporates off your body. Okay, that can fall as rain somewhere else. There's a pleasant thought for you. Okay, basically any water anywhere is going to get back into the water cycle and eventually reprecipitate out. Okay, so I don't know, maybe the snow that's on the ground now was dinosaur pee, okay, or whatever. Okay, it's all going to be recycled. It's all going to come back. Okay, most of the world's water is saline, okay, salty, 97%. So less than 3% is fresh, and 3/4 of all that fresh water is frozen. Okay, tied up in glaciers, polar ice caps, things like that. Do we depend on that 3%? Can we drink salt water? Okay, so that 97% of that water, it's no good to us. Okay, so it's a very, very important resource. Okay, but we've got a lot of this groundwater, which we've been talking about here the last few minutes. Okay, found in water-bearing porous rock. Right. So when we're talking about these wells, it's sometimes people get the wrong impression of what they look like. An aquifer isn't an underground lake. Okay, because sometimes people envision that that's what it is. What it really is like if you filled a glass with rocks and then poured water, and the water would fill the spaces between the rocks. That's what an aquifer is really like. Okay, it's water trapped between the rocks, and then you get a pipe down in there and you can pull the water out. Okay, so that's really what an aquifer truly looks like. Okay, we were talking about these glaciers here and what's happening to them. Okay, they're shrinking. Right, they're shrinking, which means a lot of the water that's stored in here is going to end up where? Where does all water eventually go? To the ocean. Yeah, okay. All the water is eventually going to end up in the ocean. So we've had all this water that for the last 10,000 years has been frozen heading to the ocean. What's going to happen to the ocean? It's going to rise. Okay, we have rising sea levels all over the world. Okay, slowly but surely the water level is coming up. Okay, which is why some places like let's say Venice, Italy, okay, the water level is coming up, and they actually have to float some of the buildings, okay, to keep them from being flooded. Okay, so there's serious issues with if the sea level continues to rise. Okay, the other problem is if it gets into the ocean, it's no more good to us. Okay, these glaciers are really shrinking. When I did this hike, this is Mount Robson here, but way down at the tongue of this glacier, it's about a kilometer down from where I took that picture. That's where the end of the glacier is. You walk another 2.5 kilometers and you get to this sign that says in 1901, the Alpine Club of Canada marked the Robson Glacier to be at this point. Okay, the glacier in 100 years has receded over a kilometer. Okay, now that's just how much shorter it's gotten. Okay, remember that this glacier used to fill this valley. So it's not just length, it's also volume, okay, that's decreasing. So they're decreasing rapidly. But of course, if they weren't melting, we wouldn't have any rivers either. Right? So it's a natural process, but it's something we got to be aware of. All right, the lithosphere. Okay, all the rock on Earth, no matter how small, is known as the lithosphere. And the most important part of that is the soil, because that's where plants can grow, get their nutrients. Okay, that's usually the top layer as well that's doing all the absorbing of solar energy. Okay, is soil the same everywhere you go? Nope. Okay, soil is different because soil comes from rocks, and rocks are different everywhere you go. Okay, around here, most of our rock is sandstone, so our soil tends to be pretty sandy. Okay, and generally kind of lighter in color. If you go further north, where there's more limestone, the soil tends to be darker and finer. Okay, just because that soil is coming from different kinds of rocks. So that wherever you go, your soil is going to be different. Okay. Now, are there layers to soil? Okay, like if you all dug a hole, right? At some point, right? You dig and then you eventually hit what's underneath the soil. Clay. Yeah, there's usually clay, and then in the clay, usually you start hitting rocks and stuff, and the further down you go, eventually you'll hit nothing but rock. Okay, depending on where you are, that can be closer to the surface than others. Okay, I know when I was putting in my fence, the bedrock was literally this far down. Okay, like I would hit it with the post hole auger every single time. I had to use lots of concrete in my post holes because I couldn't dig them very deep. Okay? Most places it's considerably deeper than that. So you have your topsoil on top that contains, the decomposed organisms and the loam and all the kind of nutrients and things like that. Underneath that you have clay, and then underneath that is the parent material. Why is the clay not on top? Water can be absorbed, and clay is really fine. So what can happen with clay is when it rains, clay particles can wash down between the spaces in the topsoil particles. So it collects down underneath. Okay? If you had a sandbox as a kid, okay, you probably found that there was clay underneath the sand. It's not because you put clay in a sandbox. It's because really fine particles can land on the sand. When rain comes, it washes them between the particles of sand because sand particles are really big, okay? And clay ends up underneath. Okay? Clay always washes down underneath and collects at the bottom because it's very fine. If you have clay that's dry and you put it between your fingers, it feels like baking soda or flour. Okay, very smooth, very fine. Whereas if you take sand and rub it between your fingers, it's coarse and gritty. Okay, the particles are much bigger. All right, so soil is the topmost layer of the Earth's surface. Okay, it is its own ecosystem, and it has both biotic and abiotic components. Okay, biotic means living things, abiotic means non-living, and we talked about those back in the biology unit. Okay, biotic and abiotic factors. All right, would you could describe this, what you see here, as soil? What does it look like mostly? Rocks. Okay, is there a plant growing in it? Then it's soil. Okay, soil isn't always like perfect, peat moss, potting soil like you buy at the store. Okay, lots of times soil can be really sandy or really rocky. Okay, if you're the right kind of plant, you can be adapted to grow in those conditions. Okay, yes, we would generally agree that soil isn't very good. Okay, it's not very nutrient rich, but it's good enough for that plant. Okay, down below here, we see kind of like a dried up lake bed or dried up riverbed here, and there's lots of white stuff on the surface. What's that white stuff? Salt. Okay, when lakes, sloughs, things like that dry up, they leave all the minerals that were dissolved in the water behind. Okay, so when it evaporates, the salt gets left, okay, and it creates this salt flat, which is really tough for really anything to grow in, because we talked about that in the bio unit as well. If you have all that salt, it's going to interfere with the osmotic pressure when you try and transport materials. So the nature of soil, the composition of soil is really important in terms of what's going to live there and how much energy is going to be absorbed or reflected. Okay, so the layers of soil are typically called horizons. Okay? The A horizon is the topsoil. The B horizon is the subsoil, so that's like the clay. Okay, and then we have the C horizon. We don't use the R. Okay, the C horizon is essentially what we call parent material. Okay, we call it parent material because it's what gives birth to soil. The rocks that are decomposing and they're becoming soil, so it's parent material. Okay, so the O horizon is the most fertile layer. That's where you would find like, dead grass and things like that are in the process of being broken down. Okay, it creates the nice loose stuff that's easy for plants to get roots into. Okay. It's also the part of the soil that's typically the darkest. It can do the most absorption of solar energy. Okay, but without soil, we don't get plants, and plants can't convert solar energy into sugars and things like that. Okay, so the A horizon, like we said, is the topsoil. It's a mixture of decomposed rock, etc. And depending on where you are, it can be really thick or it can be really thin. Okay, generally, the higher up into the mountains you go, the thinner the A horizon is. Okay, and I showed you that picture in the bio unit where I had the trowel in the ground, but it was sitting on a rock. Okay, because the soil was so thin. So in some places, the A horizon would be really, really thin. Other places, really thick. Generally, in our area, the grasslands, the A horizon is really thick. Okay, it's generally pretty thick, like a couple of feet at least. Right? The subsoil around here tends to be a little less thick. Okay, we don't have as much clay, and then the parent material is further down. And again, depending on where you are, there could be an outcropping of something, and it's close to the surface. Okay, B horizon is all clay. If you go out to like PEI, they have like the really red clayish soil. Okay, and that's what you can see here. Okay, is a soil horizon from that area. It's very, very thin topsoil, and then lots of subsoil, lots of the red clay. Anyone ever go to PEI before? Like the whole gimmick there is like the PEI dirt shirt, where they take like a white shirt and they just soak it in clay water, and it stains it, and then you get this PEI dirt shirt. It's a real money grab, tourist trap kind of thing. Okay. In the tropical rainforest, oddly enough, there's almost no topsoil because it's always flooded and it's always washing away. Clay tends to cement down and stay put. All right, we will leave it at that. Okay, and we'll go over your test on Monday. Remember, if you did write the test, your mark is already up on PowerSchool and you can check it there. If you didn't write the test, you're going to be writing it on Monday in class, Galloways.